Okay, let me welcome you to this fourth lecture of our course. This is the last lecture that is going to be of a general character. And then after these lectures, we're going to get into specific topics in more detail. So we're going to do a review of what we have done and where we are going. Then we're going to talk about problems that involve parameters that change over time. This is the subject of adaptive control, and we're going to see how we can approach it. Then we are going to go back to approximation in value space in generality and talk about another type of method for approximation called approximation in policy space. And we are going to see how these two interact with each other and can be combined. Then we're going to discuss various general issues of approximation in value space, like Monte Carlo simulation, how it enters the picture, model-free implementations, and things like that. So let's go back a little and review what we have done so far. The first 4 lectures of this class, including this one, are sort of big picture lectures, overview lectures that aim to draw the broad conceptual framework of our subject and also what we aim to do in this class. And our focal point has been approximation in value space, motivated by the alpha 0 and TD Gammon paradigms, generalized, of course. The general idea here is that we have 2 algorithms, online play and offline training algorithms, and we use online play to improve making decisions in real time to improve on the results of offline training. Now, future lectures are going to go into greater depth in selected parts of the big picture. So let's summarize our lectures. In lecture 1, we introduced alpha 0 as a motivating example, the offline training and online play portions, various generalities about reinforcement learning and its connection to dynamic programming. We developed the exact dynamic programming for finite horizon deterministic problems, and we also gave a couple of examples. In lecture 2, we went into finite horizon stochastic dynamic programming, developed that algorithm, and then we went into infinite horizon problems. We didn't cover them in real depth, but we gave an overview of the analytical aspects and the algorithmic aspects of them, value iteration, policy iteration, the like. We gave various examples, and we focused on linear quadratic problems, which is an important application for us. It is important in general, but also particularly important for our course because it provides the basis for visualizations. Then, in the last lecture, we went into approximation value space and visualizations based on Newton's method. And we did this in the context of linear quadratic problems, which are well suited for this purpose, but the ideas generalize very broadly, and on occasion, we will have opportunity to return to them. Then we gave examples of problem formulations and reformulations, the state augmentation, multi-agent systems, POM-DP, and so on. And now today, we're going to start with, we're going to complete the subject of problem formulations and look at issues of adaptive control and also model predictive control. We are also going to go into the implementation aspects of approximation value space. We're going to see that there are many different ways to implement approximation value space, and together they form a very large part of reinforcement learning. We're also going to talk about approximation policy space and the connections that it has with approximation in value space. So all of this is big picture stuff. Now, we are going to cover in more depth and detail some parts of this picture. And these are rollout that we have discussed in some detail so far. Rollout and its various variations for finite horizon, discrete deterministic, and stochastic problems. Then we're going to say a few more things about model predictive control. We're going to say a few more things about multi-agent problems. Then we're going to switch the emphasis to offline training. And we're going to discuss how you train neural networks to be used either for value approximation or policy approximation in the context of reinforcement learning. And also, we're going to discuss other approximation architectures, like architectures that involve a linear combination of features or combinations of feature-based architectures with neural networks. Then we're going to spend some time going into infinite horizon problems and develop the theory in greater detail with a little bit more rigor. And then after we have this background, we are going to use it to discuss approximate methods for infinite horizon problems. And our emphasis here is going to be on policy iteration and its various variations. It has many variations. And we're going to see that this is really a fundamental method in the context of infinite horizon problems. Then we're going to spend one lecture on approximation in policy space, the offline training of policies, selecting policies from within a parametric class, such as the one provided by a neural network, finding the parameters of that parametric class that give you policies that perform well for our problem. And methods that are used in this context are policy gradient methods and random search methods. We're going to spend one lecture on that. And our last topic is going to be aggregation. How do you simplify a problem, reduce the state space, solve that problem, and then use its solution for approximation in value space over the original problem that you started with. So we've done 4 lectures so far, including this one, and we have another 8 or 9 lectures on this topic here. So let's go into adaptive control. We have a problem where the parameters change, the parameters of the system equation, and perhaps the probability distribution involved in the problem. And so the problem is changing on us. And the question is, how do we deal with that? And how do we adapt to it? And that's the subject of adaptive control, a very old methodology with a rich history of practice and theory. Just to give you a simple example, suppose that you have a cruise control type problem where you have a car and you want to keep its velocity close to some target level that you set. 60 miles, 70 miles an hour. Now the car's velocity, a simplified model, is given by an equation like this, where xk is the velocity at time k. Now at the next stage, this velocity is affected by the current velocity. There's a coefficient a here, which is less than 1. It models things like friction on the road, wind drag, and things like that. UK is the control, the propulsive power that you apply on the car, how far you press the gas. And it has a coefficient that determines how it affects its velocity, but that coefficient depends on things like the road that you're in, whether it's uphill or downhill, the number of passengers, and all of this affect P. So as you travel on the road, these things change, these parameters change. Moreover, let's adopt a quadratic cost function, which is not unusual in this type of problem, where you want to keep the velocity close to some target velocity, a target level. This x bar is a target level that you set. And this quadratic objective penalizes deviation from that target velocity, and also penalizes large controls, okay? Both because we have a limited amount of control and also because it leads to a more smoothly functioning system. R here is some positive parameter. On the other hand, A and B change, and also X bar changes. X bar, the target velocity. Sometimes you want to go faster, sometimes slower. You have to change X bar. Moreover, in adaptive versions of this problem, there are other cars on the road. So if you get too close to another car, you want to set the target lower, okay? And perhaps there is radar to measure the distance. Perhaps there is radar to measure also to estimate the velocity of the cars ahead. And there are algorithms to change this X bar. Now, A, B, and X bar, okay? Some of them may be measured, some of them may be estimated with some error. This is a question mark as to how you estimate these parameters. But suppose now that you are able to obtain estimates of them. So how do you do in a context like this? Well, some possibilities are here. Ignore the changes in the parameters. That's one possibility. Let A and B vary, but have a controller that's robust. Works reasonably well, not optimally, of course, works reasonably well for a broad range of parameters. This is, if the parameters change a lot, then this may not work very well. However, it's still, this type of control is used quite widely in the control system design. And a time-honored methodology in this context is PID control. In PID control, there are 3 parameters that you set, and you keep those parameters the same, regardless of whether the parameters of the system change themselves. This is used very widely. It's been around for 100 years, and it has served well. However, in many situations, it's not adequate. So people have been looking for alternatives since a long time ago. So that's one possibility. Just ignore the parameters and design a controller that's resilient to changes. The second possibility is to try to estimate the parameters and then use the estimates to re-optimize or to change the controller. Now, one possibility is online replanning by optimization. In other words, you measure the parameters, you have estimates of the parameters, and you modify the controller to make it optimal for the current set of estimates. Now, this means that every time the parameters change, or the estimates change, you have to re-optimize the system. And that can be very time-consuming. It requires online system identification and optimal control computation. It has also some theoretical pitfalls that we're not going to get into. But generally speaking, this is not so easy to do. A simpler alternative is to do suboptimal replanning. Online replanning with some suboptimal control method, like rollout, with some base policy whose cost function is computed using the current parameter estimates. So again, you measure the parameters and you introduce the changes into the rollout algorithm. It will not exactly optimize the system for the current set of parameters, but it may do something close. And this is simpler, less time consuming. And let's look into it a little further. Okay, online replanning by optimization. This has the name is used widely in control theory, indirect adaptive control. Indirect because you go through system identification, parameter identification, before you change the controller parameters in response. So here's a figure. We have a system, and its state is measured by the controller, is known. It's assumed to be known by the controller. And This controller applies through a policy that it has a control at every time step. And we also get data from the system. We follow the system. We monitor it for changes in parameters. And we have a parameter estimation or system identification algorithm here that on occasion feeds new parameters as they are needed to the controller. And the controller adapts itself so that it's optimal for the new set of parameters. So measure, identify parameters, give them to the controller, and the controller re-optimizes. And like we said in the previous slide, this can be time-consuming. So that motivates using a suboptimal controller instead. For example, one that's based on approximation in value space. So here's the picture for that. Here we assume that there is an estimation cloud or system identification cloud that monitors the change in system and perhaps other things such as constraint parameters, probability distributions, and so on, and feeds these estimates into the control algorithm. And now the control algorithm is not optimal, it does not re-optimize, but does something suboptimal, which is approximation in value space. Uses an alpha 0 type of algorithm, whereby it looks ahead for several steps from the current state where it is, then uses a base policy and does rollout with that, and then uses a cost function approximation at the end. Now, this in many cases, most cases, is faster than online replanning with re-optimization. And as the parameters change, the look-ahead minimization adapts itself, but it can continue to use the same base policy for rollout. And there's also the possibility of recalculating the base policy in the background. So there are these parameter estimates that are given to this algorithm, and there's a base policy that's either given some originally computed robust policy, or it is recalculated as we move forward. So here we're not doing re-optimization, full re-optimization, we're doing something suboptimal. And the question is, how much do we lose? So let me go into an example here. This is a linear quadratic example, and we're going to look at online replanning as the parameters of the system change. Now, the example is simplified. There's only one unknown parameter, B. It's only this B that changes. And the cost function is quadratic, and we'll use an infinite horizon here so that we can use the Riccati equation calculations for this example. Now, B changes, and we use a base policy, a robust, quote-unquote robust policy that's optimal for B equals to 2. So in this example, in this figure, we have the changing parameter B on the horizontal, and the cost function, the quadratic cost coefficient of different policies on the vertical. And we have a base policy that is optimal for B equals 2. And the bottom curve here gives the cost of the exactly re-optimized policy. So this is the optimal that you can get for every possible parameter value. And the base policy is optimized for 2, but it's left at 2 as the parameters change. And then you lose that much, okay? Because this policy is not optimal for the new parameters. And it incurs a certain loss, optimality loss, which of course, as the parameters deviate more and more from the nominal value, this difference becomes larger. So now, instead of doing adaptive control by reoptimization, let's do approximate reoptimization by using the rollout policy, using this as base policy. And you see there is no difference between the two. The approximate and the reoptimization and the exact reoptimization give you the same result. And how can we interpret this? Well, we gave the reason last time. It's Newton's method. The approximate rollout policy is a Newton step. Instead of finding the exact solution of the Riccati equation, it finds it approximately through a Newton step. And what you see here is the power of the Newton step. A single Newton step is sufficient to reoptimize almost exactly the policy over a broad range of parameters. Are there any questions here?
Professor?
Yes.
So the exact reoptimized policy and approximately reoptimized rollout policy is almost matched because we can think of this is a Newton's method. This is a quadratic function. So it's almost matches. Is that correct?
Okay. The cost function is quadratic, but the Riccati operator is not quadratic. It's simply concave and smooth. The Newton step is a Newton step from the cost of the base policy to the cost of the adaptive policy. And that is a Newton step for solving the Riccati equation.
Yeah.
Of this cost to that cost. And that's not quadratic. Okay. Any other questions?
Hey, Professor, my question is, why is the curve so smooth? Why isn't there any zigzags up and downs during the optimization? It is as if the curve or the optimization knows exactly which direction to go. And why is that?
What you see here is the solution of the Riccati equation for different values of B. Now, the Riccati equation, the solution of the Riccati equation varies continuously with its parameters. So that's why you see this smoothness. I don't know why you would think that this would be zigzag. There's no randomness here. You plug into the Riccati equation a certain value of B, you get this as a solution. You get a different value, you get this as a solution. And as the parameters of the Riccati equation change, so does the corresponding solution.
So that means this is a deterministic problem, right?
Yes, it is a yeah. Besides that, we're looking at the Riccati equation, which does not involve any randomness.
Okay, thank you.
Okay. So let's look at model predictive control. It deals with a classical problem in control theory. You have a discrete time system. I'm giving you here the deterministic version. We have a deterministic discrete time system with state and control, and we have a positive cost except at 0, at the origin, okay? X is an n-dimensional vector, and we want to keep the state, xk, near the origin. That's the classical control regulation problem. So we formulated, this is a common formulation, we formulate by introducing a cost function that is 0 at the desired point, the goal, which is the origin, and is positive outside 0, okay? So we provide an incentive for the controller to drive the state of the system towards 0, where we want to be. There's, of course, also a cost of control. We want to do it with not too much control. And there are some constraints here on UK and perhaps also on XK. I'm giving you here an oversimplified version. And let's consider an undiscounted infinite horizon version of this problem. And the general objective is to keep the state of the system near 0, to bring it to 0 or keep it near 0, asymptotically make it approach 0. Now, the optimal solution of this problem can be quite difficult, particularly if you have to do it and do it again every so often. It's quite difficult. And MPC, model predictive control, in its original form, works as follows. Instead of considering minimization over the infinite horizon, we consider minimization of the cost function over the next L stages. 3 stages, 5 stages, 10 stages, 2 stages. However, we also require that at the end of the L stages, we drive the state to 0. So we are at the current state and we calculate our control with the idea of bringing the state L steps ahead to 0. Now, in the infinite horizon problem, we want to bring the state to 0 over an infinite number of steps, but this one goes L steps, which is an easier calculation. And then what we do is we obtain a sequence of controls for the first stage and for the subsequent stages. And we apply the first control of the minimizing sequence, and we discard all the other controls for this time period, then move to the next state, and then we redo this optimization L steps ahead, and then apply the first control in the optimized sequence, then go to the next stage, and so on. So we always look L steps ahead while keeping the state after L stages to 0. That's the way this works. So what is this and why should it work? Well, if you look at it, if you look at this figure, you'll see that this is just rollout. It's approximation in value space with look ahead, one step look ahead, and at the end we have a heuristic, a suboptimal policy that drives xk plus L to 0 in optimally taking into account the cost involved, and does this in L minus 1 steps, not L steps, L minus 1 steps. So there's a clear connection with rollout here, and also a clear connection with multi-step look ahead. And
Professor, I have a question here.
yeah.
My question is, what is the significance of having xk plus L being 0? In my mind, I'm trying to map this to the example of the driving car. So xk could be 60 miles per hour, right? That's the speed of the car. So why would I drop the car speed to 0?
Okay, you will not do it actually. You will do it with the purpose of calculating a control at the current stage. You'll sort of push the system in the direction of getting to the origin.
So can you use one example to describe xk and xk plus L in the car example? What is xk?
Yeah, you want to be you want to go to 60 miles an hour, and you are at 70 miles an hour. So over, let's say, 10 time periods, you want to slow down to near 60 miles. But in MPC, you calculate a sequence that takes you exactly to 60 miles an hour after 10 steps. And you apply the first term of that sequence, the first element of that sequence for the first stage. And then you redo the calculation and so on. And this calculation is simpler than solving the problem over an infinite horizon, particularly if you have constraints on control and state.
Okay, so my understanding is that xk plus L is really the speed difference, right, away from the target speed. It's a delta speed.
Yeah, if you want to connect it with the adaptive cruise control problem, yeah, you might say that.
Okay, thanks.
Okay, a nice thing to know about MPC, and in fact, an important point for its acceptance in practice, is that's very well suited for online replanning. As the parameters of the system change, you simply change this optimization. It's an online method, and it can adapt. It can do replanning on the fly. So there are a lot of other things that you can prove about this, including stability. There's a nice stability analysis of MPC that shows that the MPC controller, which is suboptimal, is still stable for the given for a given problem under some conditions that are usually satisfied. Now MPC.
Professor?
Yes.
Yeah. Like when you say suboptimal, do you mean like suboptimal as an approximation to the infinite horizon problem?
Yes.
Okay. Thank you.
Yes, the original problem is infinite horizon and has this cost function over an infinite horizon. Here we do something different, and as a result, there is suboptimality. Okay, there are many variations of MPC. There's a very wide literature, and MPC for deterministic problems, for stochastic problems, different treatments of constraints, and so on. But a major variation is the following. Instead of driving the state of the system to 0, L steps ahead, we just use a terminal cost function approximation that penalizes deviations from 0. So now what we have is an approximation in value space with L step look ahead and cost function approximation. And we can also extend the look ahead by using some kind of a base policy for rollout. And this is within this broad context. This is a broad context for applying MPC. And in fact, the MATLAB toolbox for MPC uses this type of scheme with terminal cost approximation and also with rollout, which is exactly the AlphaZero type of architecture. Okay. So now we're going to broaden our discussion and look at approximation in value and policy space. Let's go back to the stochastic dynamic programming algorithm, its exact form. It's given here. It produces the optimal costs of the tail subproblems that start at any stage and any state, going backwards, starting at the end, and going one step earlier using this recursion. First stage costs plus optimal cost to go, minimization, and goes all the way back from n-1 to all the way down to 0. And the optimal cost function is obtained at the last step of this algorithm. Now, once we have this optimal cost to go, we go forward to obtain online the optimal controls by minimizing in this expression at any state that we can be. We observe the state and we apply this control. Now, you can view this as an offline training type of calculation, and you can view this as online play using the results of the offline training. But the main difficulty here is that the offline training is just very often a horrendous computation. It's impossible to do it because the computation requirements explode as n goes to infinity, as the size of the state space goes to becomes larger. And moreover, even if you could do this computation, you would need a lot of storage for this JK star functions. The lookup tables would be too big. So the whole point in reinforcement learning is to simplify this calculation without losing too much optimality. And in particular, approximation in value space uses a J tilde function, however obtained, in place of J star for each one of these time periods. So here is a schematic of approximation in value space with one step look ahead and no rollout. at state xk, we perform this minimization involving the first step and an approximation of the future costs as represented by this J tilde function, which we assume that we have gotten in some way, we compute in some way. There are many different ways to do that. And one possibility is to get it through offline training. So we do this minimization, and the control that we use at state X is the one that minimizes here. And this is done during online play. After we do this at state xk plus 1, we go to the next state and redo it again. At each time step, we can compute a control. Now, this provides you a control to apply for every possible state and stage. So it defines a policy, a suboptimal control law, which we denote by mu k tilde. So mu k tilde of xk gives you the control that is obtained from this minimization at xk. Okay.
So,
Now,
Professor,
yes.
question here. So for this approach, you only look forward, right? One step at a time. You don't go backward because that is not achievable, right?
Yes.
Okay. And the look ahead step can be 1 or can be k or can be L, right?
Okay, in this figure, it's one step look ahead. In the next figure, it's going to be many steps ahead. And this figure, okay, there are two other slides that sort of complement this figure and draw a broader picture.
Then can I conclude that approximation in a value space is only applicable in forward-looking methodology? You only need it when you look forward. Or you only need it in combination with rule out, right? If you don't have rule out, this is not applicable.
Okay, I don't see why you bring all of these things together. There's no rollout in this picture at all. But you're right that this is a forward calculation.
Okay, thank you.
Okay, now this is an important picture with all the other stuff that I'm writing here. All together with the next two slides, it paints the picture for 80% of reinforcement learning. Just to throw a number. What we're going to be doing is fleshing out this picture and introduce the various methods that you use to compute the approximate cost to go, the J tildes, but also there's an incentive to do some further approximation here. There are three approximations. The first approximation is constructing cost function approximations J tilde. Another approximation that is often done is to approximate this expected value. Now, this expected value may complicate this minimization, may be time consuming. So sometimes it is there is an incentive to approximate this expected value, and we're going to see ways of doing that. And the third approximation is to make this minimization a little cheaper, make it, sometimes it's very complicated, and we may approximate it to make it tractable. Now, the big questions, and in fact, the focus in a lot of the remainder of this class is how do we do all these things? And there are many different ways of doing it. How do we obtain J tildes? Well, one possibility is problem approximation. You start with a problem that is difficult, and you construct an approximate version that's easier to handle, and in fact may admit an exact dynamic programming solution. How do you do this? Well, you reduce the state space, you simplify the stochastic probability distributions of WK, you may simplify the constraints of the problem, but you approximate the problem, it becomes easier, and the cost function of that approximate problem is used as J tilde here. Aggregation is a method that's based on problem approximation. But other possibilities, there are other possibilities. Various heuristics for the problem can be used to define an approximate cost function. Rollout with a base policy is one possibility, and you can calculate these values a number of different ways, analytically or by simulation, as you need them for this minimization. Here's another broad class of methods. It is based on parametric approximation and neural networks. Generally, this type of approximation require offline training. And what we do here is we have this function J tilde, which is selected from a parametric class of functions, a class of functions with a given structure, but also involving some parameters. And these parameters, for example, in the context of a neural network, may be the weights of the various layers of the neural network. Or in the context of a feature-based architecture, maybe the parameters multiplying the features that give you this cost approximation. And you introduce a parametric class of functions to approximate this target function here. And then we collect data and we do training to select parameters that give you good elements from this class. And that's what you use. So we have problem approximation, simplifications, neural networks, aggregation, rollout, and model predictive control ordinarily uses just rollout without, but also multi-step look ahead. So that's already a pretty broad methodology, and we're going to cover it selectively in various levels of depth. Here, a very common approach for simplifying the calculation of the expected value is actually very old. It was still very much around when I was a PhD student. It's called the certainty equivalence approximation. And what we do is we replace this WK that has a probability distribution that bothers us with a deterministic quantity. We simply fix it at its expected value or some kind of a certainty equivalent value. And we plug it in here, and then we get a deterministic minimization, which is simpler. So that's a certainty equivalent approach, and it has various variations. One possibility is to calculate this expected value by some kind of adaptive simulation, Monte Carlo simulation. Sometimes we simulate over, sometimes we may simulate extensively to obtain almost the expected value, but for controls that may not be very promising, you may want to do a more limited simulation. And there's a concept called adaptive simulation, whereby you simulate this expected value for various values of control, and you figure out, based on the preliminary results of the simulation, which controls are promising and which are not. And you throw away some of these controls that do not look promising and do not simulate them anymore. And that's the idea underlying this Monte Carlo tree search that we are going to discuss a little later. Monte Carlo tree search is a particular type of adaptive simulation method that has as objective to minimize this expected value. Let's go to the third approximation here. To do this minimization may be difficult for a number of reasons. It may involve a continuous control space, and we may not have a good method for dealing with that. So one possibility is to discretize this control space and reduce it into a calculation that's finite rather than infinite. Another possibility is to simplify this minimization in some way, and we're going to see that a major version of this type of idea applies to multi-agent problems, which have a particularly nasty control space involving the Cartesian product of components corresponding to different agents. We simplify the minimization using a one agent at a time type of minimization, and we're going to see that still we obtain a legitimate approximation in value space method. So that's an important picture, and it packs a lot of methods. Three types of approximations with different methods that can be applied in each one, depending on the structure of the problem. And the nice thing is that typically, these three approximations can be addressed separately. In other words, you can make combinations, a mix and match type of methodology by selecting some stuff from here, some stuff from here, and some stuff from there. So that's the big picture corresponding to finite horizon problems, one step look ahead. Okay, now we can expand this very simply to multi-step look ahead. Here at state xk, we do a minimization involving multiple steps, L steps in particular, and we add at the end a terminal cost approximation that represents, estimates the cost of future stages using this J tilde function. So we have an infinite horizon problem, but at state xk, we solve an L stage version as opposed to a one stage version of the dynamic programming problem, with xk being the initial state and J tilde k plus L steps ahead being the terminal cost function approximation. Then we obtain a sequence of controls to apply at the various stages. At state xk, a control uk, and then policies, control functions for the remaining L-1 stages. This is the result of this finite horizon problem, L stage problem that we solve. And what we do is use only the first element of this optimal sequence and throw all this mu stuff away. Now, this uk is going to take us to xk plus 1, and then we solve again an L step look ahead minimization problem and use the first element, uk plus 1, and so on. But the thing is that for any uk, I obtain any xk, I obtain uk, so that gives me the multi-step look, L step look ahead policy. And of course, we can view L step look ahead as a special case of one step look ahead. How so? Because we can lump the cost of these stages into this J tilde cost function. So it's effectively a one step look ahead approximation value space with a look ahead terminal cost approximation that involves the optimal cost function of an L-1 stages problem with terminal cost J tilde. So multi-step look ahead is a special case of one step look ahead. On the other hand, it's sometimes useful to look at it separately because it reveals some aspects that provides some insights that are special for this type of structure. But
Professor, can I ask a question?
Okay.
Yeah. Why do you use policies for the k plus 1 instead of values of, I don't know, uk plus 1, uk plus L minus 1?
If we had a deterministic problem with no expectation and no W's, we could use sequences. However, generally in stochastic problems, we need to look policies because with policies, we can get something that's better, right? That's why we use policies here, because we want to get a stochastic problem to solve with L steps horizon rather than infinite horizon. And we will get a better sequence solving this problem with control functions, view it in other words as a stochastic dynamic programming problem rather than view it as a deterministic problem and obtain a sequence. It's the power of feedback. We want to get this muse to involve state feedback in order to obtain a better sequence for this minimization.
Thank you.
Okay, so the last point I want to make here is that it's multi-step look ahead, but there are still 3 approximations that can be used. One right here, one right here, and one right here. And again, these approximations are largely independent. The only difference between this and the previous one is the length of the look ahead. And of course, the difficulty in doing this minimization as the length of the look ahead increases. Okay, so the preceding 2 slides showed approximation in value space for finite horizon. We also have approximation in value space for an infinite horizon. Here, okay, the cost function is stationary, the system equation is stationary, and we have cost approximation. Let's consider a discounted problem where the discount factor in the optimality equation comes in here. And what we do at a given state X, we minimize the cost of the expected cost of the first stage plus the discounted cost function approximation for the remaining stages, starting from the next state. And there are still 3 approximations to consider here: J tilde, expected value, and the minimization approximation. There's also, this is for one-step look ahead. For multi-step look ahead, L-step look ahead, we solve instead an L stages minimization problem with this terminal cost function approximation. And we apply the first control. We get this UK at the state XK. And then we go to the next stage and so on. So this is very similar to the finite horizon case, except that what we have here is stationary quantities that don't change over time. The state and control spaces are the same over time, and that's about it. Okay, so whether you're looking at this figure or whether you're looking at this figure or whether you're looking at this figure, you obtain a look-ahead policy, a suboptimal control law, which assigns a control mu tilde k of xk at state xk. So this is the look-ahead policy that you obtain. And the question of interest here is, how do these j tildes relate to the cost function of this suboptimal control law? We want this cost function to be small, to be good. How does the choice of j tilde affect the quality of the look-ahead policy that we obtain? And this is where the Newton interpretation comes in, and that's what we talked about in the previous lecture. There is this figure which relates j tilde to j mu tilde, the cost approximation that you use in relation to the cost function of the look-ahead policy. Okay, let me spend some time here on this figure. It involves the Bellman operators of the problem, which in the previous lecture where we talked about linear quadratic problems were the Riccati operators. This is the min Bellman operator, and this is the mu Bellman operator. A fixed point of t is j star, the optimal cost function of the problem. And we visualize this by drawing the graph of this t operator, the red graph. We intersect it with the 45-degree line, which is the graph of j. And we find the point where the two intersect, and this is where j tilde lies. I'm sorry, this is where j star lies. J tilde can be something different. If we knew j star, we would use it, okay? But we don't know it, so we start with some j tilde that may be to the left or maybe to the right. And we do approximation one step look-ahead minimization. And it has this interpretation, which is very general, because this Tj is always concave within our context, and this T muse of j is linear. And what we obtain by minimizing in this equation here with j replaced by j tilde is this tangent policy, mu tilde, which has a graph like this, and its cost is given by the fixed point, the intersection with the 45-degree line. And what this is a linearization of the Bellman operator. We solve the linearized problem to obtain its solution, and this is just what Newton's method does. So passing from a cost approximation j tilde to the cost function of a one-step look-ahead policy is a Newton step. And the idea here is that if you manage that Newton steps are very effective if j tilde is close to j star. And the closer they are, the closest j mu tilde is going to be j star. If j tilde is within the region of convergence of Newton's method, then you have an excellent prospect for obtaining a good look-ahead policy. Okay, so that's the interpretation. We're not going to focus on this for analysis, but it's always going to be in the background, interpreting why some results hold and some do not hold, and why some methods are good and some other methods are not so good. And speaking of results, let's look at what we can get from this picture. This picture, of course, is about performance estimates. How does the one-step look-ahead scheme perform? And the Newton step provides a local estimate. Okay, the Newton step takes j tilde into j mu tilde, and it is governed by a local and superlinear convergence estimate, at least which is local in the sense that it holds for j tilde near j star. It has this form. It says that the a priori error between j tilde and j star gives you an a posteriori error after you do the one-step look-ahead minimization that is tiny relative to that. This is a constant times this, but the constant is very small and tends to 0 as j tilde approaches j star. That's the meaning of a superlinear performance. So once you're close, error is very, very small. You're almost optimal. And we saw this with this adaptive control example that we gave earlier. On the other hand, when j tilde is far from j star, then this difference can also be large, and it can even be infinite when mu tilde is unstable, okay? So this type of estimate is valid and makes sense only when you're close to j star. Now, how close is unclear for a given problem, but this is a starting point for interpreting behavior. Now, in reinforcement learning, you'll see a lot of other estimates for one-step look-ahead that are global. In other words, they do not depend on j tilde being close to j star. They hold for all j tilde. One of the most popular ones is this one here, where it gives a bound on the cost function of the one-step look-ahead, of the L-step look-ahead policy that depends on the error between cost approximation and j star. And this is valid for alpha discounted problems, finite state, finite control, alpha discounted Markovian decision problems. This is the estimate that you're going to see in textbooks. However, I want to argue with you that this is not a very interesting estimate. And I say this with some sadness because I had I had a hand in developing estimates like that. For example, in my book with Johnson Cyclics, we have a lot of these estimates for this context and for other related contexts, and they always have this constant factor here that has in the denominator 1 minus alpha or 1 minus alpha square, which can be very, very big if alpha is close to 1. Generally speaking, this type of global estimate, which is the standard in reinforcement learning, tend to be overly conservative. They're conservative because they hold for the entire range of J tilde, close to J star and far from J star. And they are not representative of the performance of approximation in value space schemes when J tilde is near J star. So what's happening, this type of estimate is interesting when you're far away from J star, but once you get close to J star, then it is this estimate that's the one that's interesting and descriptive of what's happening in practice. And to give you an example where this estimate is really bad, let's consider a finite spaces, state and control spaces, alpha discounted Markovian decision problem, where mu tilde can be shown to be optimal if J tilde is close enough to J star. Okay, this is a result. If you can show that if you choose J tilde within some neighborhood of J star, some small neighborhood, then what you get, the mu tilde that you get, not only satisfies this relation, but is satisfied with 0 here. It's exactly optimal. So this global performance bound near J star is way off. Doesn't tell you anything that's useful or even something on which from which you can get intuition. And what's happening here, okay, for those of you who have looked into this Bellman equation and Bellman operator stuff a little more closely, what's happening is that for this type of finite spaces, alpha discounted MDP, the Bellman operator is piecewise linear. So the Newton step is exact, finds you the exact optimal solution if started within a neighborhood of J star, within which the linear pieces that are active do not change, basically. We're going to get into developing estimates like that in later when we talk about infinite horizon problems and we see how they come about and how they relate to one-step look ahead and how they relate also to policy iteration. But then again, we're going to bring up the point that these are global estimates that are very pessimistic and they are not representative of practical behavior. Okay, are there any questions?
Professor, if you don't mind, I want to ask my earlier question.
Okay.
I think I'm conceptually confused between one-step look ahead and rollout. My understanding is the one-step look ahead is equal to rollout. In other words, for me to look ahead one step, I cannot just make one choice. I have to roll out so that I have equal opportunities. That's why I think we are confused.
Yeah, I can see why you're confused. In the approximation, the general approximation in value space scheme that we have been discussing, there is one-step look-ahead minimization. Minimization is a key word here. One-step look-ahead minimization, and the remainder is rollout with a given policy. You don't minimize over different policies in the rollout part. This is for one-step look-ahead with rollout. One-step look-ahead, multi-step look-ahead with rollout involves L-step minimization. Again, minimization is a key word here. After that, it's rollout with a given policy, a much cheaper computation. So that's the difference between the two. And that's the best way I can explain it.
Okay, thanks, Professor.
Okay. Okay, so let's take a break now, and I want you to consider the following question. The general question is longer look ahead better than shorter look ahead? Well, in our discussion, we have been treating it as being better, okay? Certainly, long look ahead costs more to implement, more computation than short look ahead. On the other hand, is it always better? I say it's usually better, almost all the time. Think of AlphaZero, the chess program, with one step look ahead versus many steps look ahead, like 20 steps ahead, 30 steps ahead. I can tell you that chess players know very well that the longer you look ahead, the better moves you're going to select. However, from a theoretical point of view, it's an interesting question. Will longer look ahead produce a better policy than shorter look ahead? So I want you in the next 15 minutes of the break, if you wish, to look at this question involving this simple problem. This is a problem involving an initial state, 4 stages. However, there is a choice only at the first stage. In the first stage, you either choose between this branch or that branch. And after that, you are forced to follow, without any choice, this path here. So you have to compare this path and this path. And you can see by looking at the numbers, particularly this 10 over here, that the top branch is better than the bottom branch. However, so that's the optimal solution. This is the optimal path. On the other hand, let's try to use 2-step look-ahead minimization and 3-step look-ahead minimization with terminal cost function approximation 0, okay? Let's do this calculation without any rollout and stuff like that. Just 2-step look-ahead and then take 0 cost, or 3-step look-ahead. And see which of one of the 2 policies, the 2-step look-ahead and the 3-step look-ahead policies comes out better. And let's discuss after we convene back again in 15 minutes, which would be, it would be 2 minutes to 5 in Arizona. So we had this challenge question, and does anyone want to describe what's happening in this figure here and how to compare 2-step and 3-step look ahead?
Professor, can you hear me?
Yes, please. I can hear you very well, but go ahead.
Okay, so here the 2-step look ahead is giving us the optimal route, but the 3-step look ahead is giving us the suboptimal. And this is happening because the one cost that is actually the 10 units is actually after the 3-step, the 3rd stage. That's why the 3-step look ahead is not being able to capture that.
Yes, that's exactly right. You have explained it correctly. Generally speaking, longer look ahead is better, but not for this example. It's an exceptional example that is somewhat artificial, but you're right. 3-step look ahead looks 3 steps ahead and then looks at the cost to go from, oh, I'm sorry. Okay, in 2-step look ahead, I compare this branch and this branch, 2 steps ahead, and then I add a 0 terminal cost. So I find that the optimal branch is preferred. So 2-step look ahead finds the optimal first solution and then follows the path to the end. Now in 3-step look ahead, we look at these 3 states that are, these 2 states that are 3 steps ahead, and getting there has cost 3, getting here has cost 2, and then when adding a 0 terminal cost, I prefer this suboptimal branch. And what's happening here is that multi-step look ahead has perhaps sometimes problems with edge effects. What's happening at the edge of the look ahead? In this case, at the edge of three-step look ahead, there's a bad transition waiting to happen, but we never take it into account. We just look at the three transitions here. On the other hand, with two-step look ahead, I look up to here and up to here, but the suboptimal policy happens to have a small transition cost waiting after that. And okay, so this branch is preferred than this. And basically, it's the difference between this transition being 2, having a larger cost than this transition, but the bad transition for the suboptimal policy happens after the reach of the three-step look ahead. So that's an artificial example, but it's also interesting to have in mind that there is no theoretical result that says that longer is better. Okay, now let's consider broad issues about approximation value space. In particular, let's look at multi-step look ahead with deterministic optimizations. Remember, multi-step look ahead involves an L-step minimization and then cost function approximation after that. So if the problem is deterministic to start with a finite control space, this look-ahead minimization involves a shortest path problem with this type of tree, where at each state we have the finite number of possible controls leading to next states, and then again a finite number, and all of these transitions are deterministic. And so it's a shortest path type of problem, and it's an easy minimization. That's the big advantage that you have with deterministic type of problems. In min-max type of problems like alpha 0, we also have this advantage, type of advantage. By contrast, if the problem is stochastic, then the expansion factor of this tree grows very quickly because of the stochastic transitions, which is why TD gammon for the stochastic game of backgammon does not use long look ahead, because the computations very quickly become formidable with the increase of look ahead. Okay, if the problem has a continuous state and control space, then the L-step look-ahead minimization is a continuous optimization. It's not a shortest path type of calculation. But sometimes it can be solved quickly by continuous optimization techniques like nonlinear programming, and perhaps also integer programming. And in model predictive control, that's an important issue. How do you choose the L-step ahead minimization method so that you can do the online calculations in time, taking into account the real-time constraints of the problem? In a stochastic problem, there is also a possibility of doing the log-ahead minimization by something called stochastic programming. This is a mature methodology in optimization, which applies here, and it's more like a deterministic optimization method in its essence than a stochastic dynamic programming type of method. That's a possibility which we're going to discuss later. Now, here's a suboptimal possibility that's interesting. Suppose you have a stochastic problem with finite state and control spaces, and you're looking at L-step look ahead. Now, suppose you do the following approximation. You split the look ahead minimization into a first step, which is stochastic, and then a deterministic remainder, for example, by using certainty equivalence. So now what happens is that there's a deterministic shortest path approximation for the steps after the first. And this is easier than having a full stochastic problem for all the steps. On the other hand, it retains the advantage of the Newton step, because remember, the Newton step is the very first step, and the remainder is approximation, cost function approximation. So this type of technique works much better from the point of view of performance than converting this L-step minimization into a deterministic optimization by certainty equivalence. Okay, so that's one issue here that enters the calculus of how we implement these methods. Now let's go into a conceptually different type of approximation. Approximation in policy space. This is a major alternative to approximation in value space. And the idea here is we have a system, we measure the state, and we apply a controller which we choose from a restricted class of policies, usually a parametric class that involves a parameter RK. An example is a neural network that provides you of maps from XK, from state to control, that depend on the weights of the neural network. And in approximation policy space, involved in such a parametric family of policies, we optimize with respect to the parameters so that we get a controller that's good for our problem. Now, of course, an interesting question of what kind of method we're going to use for this optimization. And there are methods based on random search, searching within the space of parameters, semi-randomly, with some purpose, of course. Policy gradient methods, where we move RK in desirable directions involving the gradient of the cost function with respect to RK. There are classification methods that I'm going to discuss in future lectures, but also briefly in the next slide. All of these are machine learning methods for training control functions so that they achieve a useful objective. Now, suppose that you have performed this training problem and you have determined these parameters. There's an important advantage then, that the online computation of controls is much faster. Once you have computed offline these parameters and you have this controller, then finding a control in response to a given state is very quick. Just feed it to a neural network, feed the state to a neural network, and instantaneously it computes a control to apply. However, it does have an important disadvantage. All of this approximation in policy space has to be done offline. So if the problem changes on you, you cannot do online replanning. And there's no Newton step to take advantage of. So now let's look at approximation in policy space in conjunction with approximation in value space.
Professor?
Yes.
Could you do an online replanning by considering the parameters R as controls, or it doesn't make sense?
Well, it's very difficult because this training takes a long time and you don't have enough time online usually. If you apply decisions, say one every week, then you do have time. But if you apply decisions one every minute, you don't have time because this is a difficult training problem.
Okay, thank you.
So ordinarily, approximation in policy space is viewed as an offline training process. And as such, it's not suitable for online replanning. But okay, it depends on the circumstances also. Okay, so we want to connect approximation in value space with approximation in policy space. How do we go from values to policies? Well, suppose that you have approximate cost functions, J tilde. These define a suboptimal policy through one-step or multi-step look-ahead minimization. However, how can we store, how can we represent this mu tilde k function? It may be, it's defined for every state, but how do you represent it and use it on approximation in policy space context? So one way to do this is to take this one-step look-ahead policy and approximate it by using training, using data. So you generate data pairs of states and controls, where this is U case of S is the control that corresponds to state XKS through one-step look-ahead. Remember, we have J tilde, and we look at many states. We sort of sample the state space with a sufficiently rich number of states, and we do this calculation offline. So we obtain data of state control pairs. This is not the entire control function, the entire policy, but it is data relating to that policy. And then we do some kind of training offline to obtain an approximation in policy, to obtain an approximation to this mu tilde policy. As an example, suppose you have this data pairs, you use a machine learning type of algorithm. We introduce a parametric family of policies, for example, through a neural network with RK being the parameters, and then we estimate the parameters by fitting the data that you have with the result of the parametric policy. So we find R, which we call RK, the parameter RK, that makes a good fit between data and functional form of policy. This type of least squares type of problem is typical of classification methods in machine learning. Basically, you view the controls as categories, as classes, and you assign to every X a category, which is a control. And there is a connection between policies and classifiers, which we're going to go into later. But the important point that I want you to get out of this is that we can pre-compute offline policies starting from cost approximations by generating data and doing least square fits or other kind of approximations, machine learning type of approximations. Now, one thing to note here is that the Newton step interpretation is lost. Once you pass into this kind of approximation based on least squares fit, the policy that you have and its cost is not obtained by a Newton step. So something is lost here, and it's not entirely clear what. It depends on the quality of this least squares fit, but it's something to be concerned with. Okay, so here's how we go from J tildes to approximations of mu tildes. Let's go the other way too, in the other direction. How do we go from policies to values? Well, we know a way to do that is by rollout. We use some policy as a base policy, perhaps obtained in some other way, like approximation in policy space, perhaps some heuristic. And we use one step or multi-step look ahead approximation, where J tilde is the cost function of that policy. So the policy is the truncated, perhaps truncated rollout policy corresponding to this base policy. So you start with a base policy, generate cost functions of the corresponding one-step or multi-step look-ahead policy. And now, how do we represent this policy? We can't store it very easily if we want to go into, if you want to use it in an online fashion. So how do we compute that? Well, for deterministic problems, we run pi from xk plus 1 to the n, and we accumulate stage cost. For stochastic problems, we may use from xk plus 1 Monte Carlo simulation many times and average the results to obtain these values here. So now we can use this as in an offline training method to obtain new policies. We can go from policies to values and then to new policies. And that's the idea of combining approximation in value and policy space. We have seen this figure before in the context of approximate policy iteration. We have a base policy. We simulate it, and we approximate it by doing a least squares fit and obtain, and then we obtain data using that policy, and then we use approximation in policy space. So from a policy, we go to an approximation in value space, and from approximation in value space, we obtain a new policy by training a classification or policy gradient or whatever you want to use, and then that gives you a new policy which you can use as the new base policy at the next iteration. So that's how these two couple, and that's the way it's done actually in AlphaZero. A base policy translates into a cost function, and the cost function produces through rollout and multi-step look ahead a policy which is approximated again by a neural network and back again. Now, if there were no approximations and the policy iteration method were exact, then we would obtain a cost improvement. The new policy would be better than the original policy for every state. So the algorithm is capable of self-improvement and self-learning, and it's the natural extension. Its natural extension to infinite horizon problems, the policy iteration method. This is for finite horizon problems. It's inequality, but it also holds for the infinite horizon version, which is policy iteration. Now, if you have approximations in value space and policy space like you have here, this property does not necessarily hold. And there are some error bounds that relate the cost function of the rollout policy with obtained by approximation and the base policy. And we're going to get into those a little later. There are also many variations of this scheme. Optimistic policy iteration, policy evaluation methods based on temporal differences, methods of Q-learning, and so on. All of this is part and parcel of the reinforcement learning methodology. Some of this we're going to cover, and some of it we will not have time. Okay. So now let's look at some other general issues of approximation in value space. And let's return to our figure. This is the figure involving one step look ahead without rollout. And but it applies also to multi-step look ahead. And there are these various approximations, and some of these approximations may have to be done online, and some others may be done offline. So in reinforcement learning, some methods are characterized sometimes as offline methods and online methods. There is no real purely offline method or purely online method. There's always something that you have to do offline before you do anything online, and vice versa. On the other hand, we can talk about methods that are primarily offline. Most of the computations are offline. And these are characterized by things like these J tilde functions are computed by some kind of training, neural network training or some other training. Base policy may be involved, but the main thing is that these J tildes are mostly computed offline. And examples of this are when a neural network is involved. Aggregation is also an offline type of method. Also, approximation in policy space to obtain policies to roll out is again primarily an offline method. Now, the online methods, primarily online methods, are the ones for which these values are computed as needed, only at the relevant next points, and they are used online to compute the control at the n-type steps of the horizon. Examples are rollout, where you compute these values by doing simulation forward the base policy. MPC is also primarily an online method because it doesn't rely too much on offline training, and most of the work is done through the look-ahead minimization. Other things that contribute to an online character of a method, if there is approximation of this expected value. This has to be done online. Sometimes this approximation of the minimization is also an online operation. So depending on where these parts of the scheme are done, we can have offline and online methods and mixtures of the two. Okay, let's focus on simplifying the expected value calculation. Let's consider a case where we're given these probability distributions, but they are difficult, but they can be used to calculate expected values, but this calculation is difficult. Then we can modify the probability distribution to simplify the look-ahead minimization and the calculation of the expected value. And one possibility that I mentioned earlier is to replace the uncertain quantities with deterministic nominal values. Then what happens is that the look-ahead minimization problems become deterministic, as I mentioned earlier. So they could be solved by shortest path type of methods or special methods, that deterministic type of methods. The advantage here is that deterministic multi-step look-ahead minimization for deterministic problems is much simpler. So what we do here is replace the random quantities with deterministic quantities and make the calculations deterministic and simpler that way. Another type of well, in this context, we can determine nominal values the parameters by using forecasts or by using their expected values, a common approach in probabilistic approximation. And we can also, if we have forecasts that change over time, we can update the policy as the forecasts change, and it's a form of online replanning. Now, a major possibility for probabilistic approximation is when you have POM-DP, in which case the real state of the system is the belief state, the probability distribution of the current state, but that's difficult to handle in dynamic programming computations. So we use deterministic substitutes that are state estimates. So you turn the problem into a perfect state information problem using perfect state information calculations by using deterministic substitutes to the belief states. And there are some variations here involving so-called partial certainty equivalence, where some of the uncertain quantities are fixed at nominal values. They're made into deterministic, and some others maintain their stochastic character. And that may simplify the expected value calculations. And a generalization of certainty equivalence that I mentioned is to approximate the expected value by limited simulation. If you were to do exhaustive simulation by Monte Carlo method, you would obtain the exact expected value. If you take just a few samples, you can approximate the expected value with the corresponding limited sample average value. So all of these are tricks that you can play within the context of approximation in value space, but there's always a price to pay in that they introduce approximations that you'd have to judge in a given practical context whether they're serious or not. In reinforcement learning, a lot is made about model-based methods and model-free methods. Generally, when you hear the term free, you ought to be a little suspicious. Is it good to be model-free? What's the price to pay for the free? Usually they don't tell you what the price is, but there's always a price. There's no free lunch. It's always a price for something that comes free to you. Now, in this context, a model-free method is one that does not use a mathematical model. And a model-based method is one that there is a mathematical model. There are system equations, there are probability distributions. If you have them, my suggestion is that you should use them. However, if you don't have them, you may consider a model-free alternative. Now, the important thing to keep in mind for this course is that all our methods are model-based. But the model may not be a mathematical model. Maybe it may be a computer model. And I'll give an example a little later. Of course, a computer model implements a mathematical model, but it's sometimes easier to construct than a mathematical model. Now, when you have a computer model and you use simulation, this is useful when the mathematical model of the probabilities of the underlying the problem are not available, but you have the simulator, and then you can simulate sample transition probabilities. And in principle, in fact, using the simulator, you could compute these quantities here, although that may not be the best way to proceed. So that's one context where you want to use a Monte Carlo simulation approach and a computer model. Sometimes Monte Carlo simulation enters reinforcement learning for a different reason. You may have a problem that's perfectly deterministic. However, you may want to use Monte Carlo simulation in order to compute things like a large sum of numbers. That may be an overwhelming calculation, but you can use Monte Carlo estimation to approximate the sum of numbers. Similarly, if integrals are involved, people often use Monte Carlo integration to approximate a difficult to compute integral by sampling. This also happens in a number of contexts, and that's another context where Monte Carlo simulation is useful. So now let me give you a context that often arises in reinforcement learning. Now, remember that in approximation in value space, at a given state xk, you minimize this quantity with respect to u to get the one-step look-ahead policy. Now, this is with a given j tilde. So given j tilde, you want to perform this minimization. There is also a multi-step analog, but let's focus on one-step look-ahead minimization. How do we do that if we don't have a mathematical model for G and we don't have a mathematical model for F? And we also don't have a mathematical model for the distributions of WK. That's where we can use a model-free approach involving a simulator. So here it is. Remember, we have J tilde, we have computed somehow, or we use some kind of heuristic J tilde. And what we want to do is compute for different values of UK, and for a given xk, we want to compute this quantity here. How do we do it by simulation? Well, suppose that we have a simulator that when you feed it a state and you feed it a control, it generates a new state, taking into account of whatever stochastic quantities are in here, and also produces a transition cost. So these are samples, perhaps probabilistic samples corresponding to state control pairs. So we use the simulator to collect a large number of representative samples of state control successor states and stage cost quadruplets. So these are samples. We collect a lot of those. And what we want to do is construct samples of the Q factor from the preceding slide. We want to construct samples of this. And we get samples of that for given X and U. So these quantities here, cost plus cost to go for the sample, is viewed as a sample Q factor. And we collect lots of those, and then we fit them to some kind of parametric architecture. We introduce a parametric family of Q factors that depend on state control and also a parameter. And through our least squares fit, we fit the Q factor samples to the parametric family to obtain the optimal parameters by solving this least squares problem. And then we have approximate Q factors, which we can use online to calculate controls. If we had the exact Q factors, we would obtain the exact one-step look-ahead minimization policy. However, this is an approximation that is convenient in some ways because this minimization is very fast. Once you have trained offline this Q factor and you have obtained this parametric approximation, then this minimization may not be very difficult. On the other hand, here you don't obtain the one-step look-ahead policy. You obtain an approximation to that, an approximation from some parametric class, from something given by like a neural network. And this least squares fit here introduces error, and the Newton step property is lost. You can't expect this kind of policy obtained through this simulator model-free training to be equally good in quality as what you would obtain by honest to goodness one-step minimization with the exact cost per stage and the exact cost function and the exact system function. So model-free is nice because sometimes it's easier to use a simulator than construct a mathematical model of the system. But there's something to lose in all this. And one of these things is the Newton step performance guarantee, the performance bound, the superlinear performance bound. Okay, so this was our last slide. Are there any questions? Okay, so starting with the next lecture, we're going to get more in depth into various topics. Our objective is to fill out this figure here, and its infinite horizon version. We're going to talk about various ways to compute J tilde, various ways to do this minimization, and various ways to approximate. We're not going to cover these topics fully over time, but one by one, we start checking out various possibilities. And next time, we're going to talk about deterministic rollout, and also a form of rollout where you have made a certain equivalence approximation so that this minimization here is deterministic, which also relates to a problem approximation with certain equivalence. We replace the original problem with a deterministic problem. So that's the rollout is an algorithm that very useful, very reliable, and becomes an important part of more complicated algorithms. We're going to talk about it. We're going to discuss issues like under what circumstances is the rollout policy a better policy than the heuristic that you start from. We're going to look at the variations. We're going to focus on finite state deterministic problems that arise in combinatorial settings like the traveling salesman problem. And we may have time to go a little bit into stochastic rollout for stochastic problems. There will be no homework for this week. There will be a homework announced at the lecture next week. And there's a video lecture that will covers reasonably faithfully these topics from 2021. So that's all I have for today. Are there any questions? I have a question here in the chat. It has to do with the homework, which is due today. The homework had to do with a comparison of a rollout policy for a stochastic problem with the base policy. And the question has to do, how do we do the Monte Carlo simulation? Do we program the Monte Carlo simulation? Yes, you have to program the Monte Carlo simulator. Of course, it's a simple programming exercise, but you should get many samples to obtain faithful Monte Carlo estimates. And perhaps an interesting exercise would be to see how the accuracy of the Monte Carlo simulation affects the quality of the rollout policy that you obtain. Okay, so if there are no questions, we'll adjourn and get together next week.